Alright, so in this problem, we're going to be piecing together a cylindrically symmetric magnetic field, and we're going to do that in a really sort of a weird way. So let's take a look at this problem. We're given two things. We're given that we have a cylindrically symmetric magnetic field in a current-free region. Strong emphasis here on this current-free part. Okay, we're also given the z component of our magnetic field, which is just some constant c times z. And so the problem we have here is we want to find the other components of this magnetic field, mainly being bs and b phi. And then what we're going to do is we're going to take all of these together and add them up to get our main B field. All right. And so you may be thinking to yourself, well, how can we go about figuring this thing out? But one of the things that we know with it being a current-free region is that both the divergence and the curl have to be 0. Okay? And so when we examine our divergence and our curl, we can start to begin piecing together these things. So let's start with the divergence, because it's a little bit simpler. And we're going to start with that. So let's get rid of this guy right here. And so we know that 0 is equal to del dot B, and our divergence formula in cylindrical coordinates goes like this: 1 on S partial S BS partial S plus 1 on S partial B phi partial phi plus partial BZ partial Z. And we know what BZ is. BZ is given right here as CZ. And so, so pretty simply, we know that this partial derivative has to just be C. Okay? And so we know then from there that one of these other two terms here either has to sum to minus C, or just one of them has to be minus C, so that we can still be equal to 0. Okay? Now, one of the things that's pretty straightforward about this is that if we consider a cylinder here, let's draw out a simple cylinder. Oh boy, that is not a good cylinder. All right, it works. If we draw a simple cylinder like this, we know that the phi component of this is going to go from 0 to 2 pi if it's a full cylinder. Okay? And if we think about our unit circle here, 2 pi and 0 for any angle that we give is going to give the same is going to give the same value. So there should be no change in phi, all right? And so based on that, this term has to go to 0. So we're left with only needing an S component, all right? So let's examine this S component a little bit more. We know that 0 has to equal 1 on S partial S BS partial S plus C. And we need to get a minus C out of this, so we can try a few things. All right, we see that we have an S in here, and we could take a derivative of that. So if we set BS equal to a minus C, well, then we're going to get, for this guy, if BS equals negative C, we're going to get a minus C on S for our S component. That's obviously not going to result in 0, so that doesn't work. How about if we try BS equal to minus CS? Okay? Well, then with that, we're going to end up for this term right here getting a negative 2C. Okay, so now we fixed this extra S term that we have, but now we have this extra factor of 2. That's not going to give us 0. So again, that doesn't work. What about if we try BS is equal to minus CS divided by 2? That should take care of everything. And when we evaluate that, then we would get a minus C out. So we know that BS has to be minus CS per 2. All right, so now when we piece this all together, we're going to get that our total B field is equal to our BS component plus our B phi component plus our BZ component. And we know all of these now. We know that this guy is 0. We know this guy is given to us already, and we just figured out this guy. So our B field is going to be minus CS divided by 2 S hat plus 0 phi hat plus CZ Z hat. And this is our magnetic field. We just pieced together this cylindrically symmetric magnetic field in a current-free region with just knowing one original component.